This is N number 21. We are looking at tangents and arcs, and we are going to learn something else called secants later. Secants and tangents are two different things involving lines and circles here. Rules are going to get kind of iffy because there are a lot of them, and so it's just all about recognition of stuff. And before we looked inside the circle, now we're actually going to look outside the circle as well and say how it matches with things inside the circle. Before I begin, I do want to make sure that I remind you, a circle with a center here, if a tangent line, which is a line that hits only at one point on the circle, if a tangent line crosses through or hits the circle at one point, the center and that tangent line meet at a 90-degree angle. So it doesn't matter where that tangent line is, as long as it is a tangent line, it hits the circle at one point, then they meet at 90 degrees. So that's something I want you to remember. And I'm actually going to jump around this stuff. I'm not going to use this example here. Let's see, or am I? Let's see, where's AD and AF? AD, AF. Okay, never mind. I just forgot what I said. Okay, let's go and get started here. What we're going to look at here is a picture of a satellite looking at the Earth. Now, the Earth is looking from the top down. Normally, you see the Earth as, if this is a globe, here's the equator, here's the North and South Pole. We're not looking at it this way. We're looking at it from the top down. So here, this is the North Pole. The South Pole is unseen. You can see this is North America, here's Asia. And it's funny, actually, how much you don't realize how close, or how much, you didn't realize until now how close Europe, or Asia, Russia, and Alaska are together. Because normally you see the maps the other way. Anyway, I digress. Let's go ahead and get started here. Draw a quadrilateral AEDF that connects satellite A. So here's satellite A right here. I want to use that as point A. The important concept with this entire thing is you're going to see that if you're in the satellite and you're looking out at the Earth, there's a certain place that you can look out to. You can look from here. You can scan all this part of the Earth and such, whatever, or pretend like you can only see the rim here dead on. What you can't see is anything beyond that. Like, I can't see beyond this stuff and over here. So pretend like you can only see the rim. How far out can you go? Well, here, can't see the Earth. Here, boom, you look out. You can tell, I can't see this part of the Earth. And same thing over here. I can't see this part of the Earth right here. The only part that I can see is what I'm going to put in green right here. This, you can call it a minor arc, it doesn't matter. All I can see is this part of the Earth, and obviously some portions here as well. But just looking from the top, pretending like the rim is the only visible stuff, that's all I can witness. Okay, here's the center again. This is the North Pole. I want us to be able to look at A. We have to draw a quadrilateral A, D, E, F. So here's A, here's D, here's E, here's F. Okay. This quadrilateral here, we have to assign it by name. We have to figure out what it does, what the relationship is, all that good stuff. So let's go ahead and make that thing a little bigger. Now you'll notice DE is a radius. FE is a radius. Oh, that didn't really come out right. Still not coming out right. There we go. AF and AD are tangent lines. Okay, so let's start talking about relationships and all that stuff we can do. First of all, radius merged with tangent line. Here's the radius, here's the tangent line. This must be 90 degrees. ADE, or angle D, is 90 degrees. Angle F is also 90 degrees for the same reason. These have to be tangent lines here. So, or tangents with radius make 90 degrees. Now they say, if the measure of the angle at satellite A is 90 degrees, what's the measure of the equator's arc that's in view? So breaking down this problem here, the question, it says, if this is 90 degrees, they want to know what this is right here, what the measure of the arc that's in view is. Okay? Now if you forget, a circle that has a center, you draw a central angle to that, its intercepted arc is the exact same measure in degrees as its central angle. So the important thing here is here's the intercepted arc of this central angle. So if I find this angle here, I will find the measure of the intercepted arc. And the way to do this is quite simple, actually. You look at all the angles of a quadrilateral have to add up to 360 degrees. Try not to confuse it with a triangle that has to add up to 180. So quadrilateral has 90 plus 90 plus 90 plus x equals 360. Add those up, you get 270 plus x equals 360. Subtract 270, you'll get x equals 90 degrees. This is actually a rectangle, or better yet, it's actually a square. But that's besides the point. We're going to make sure that we know that. So x is 90 degrees. So angle E is 90. If this is 90 degrees, then its intercepted arc is also 90 degrees. So the answer here is 90 degrees. Excuse me. We explained how we know by figuring out the rest of it. These are tangent lines with radii matching up their 90 degrees. They tell us this is 90 degrees. Therefore, this is. Therefore, this is. Okay, what's the relationship of AD and AF? Prove the relationship using congruent triangles. So this will be an important concept that we'll talk about. First, I'll do the proof, and then we'll say, okay, what that means in the end. But here's what we are talking about. Here's a point out in space, literally. This satellite is out in space. It's outside of the circle. We're drawing two tangent lines. Okay, tangent line here, tangent line here. Now those keep going out forever. The fact that we drew a quadrilateral and it's no different. But where this point intersects with the circle, the relationship between this segment right here and this segment right here is going to be crucial. It doesn't matter where this point is. As long as they are tangent lines, there will be something very unique about them. So I want to know what the relationship is between this segment and this segment right here by doing a two-column proof. Let's make congruent triangles here. So statements and reasons. To make the triangles congruent, if we make the triangles congruent, then we can make the segments congruent by CPCTC. Using that again. Okay, let's start listing some givens here. Now, first of all, what I want to be able to do is prove that two triangles are congruent. So I'm going to go ahead and match up this purple triangle right here, ADE, with this yellow triangle here, AFE. When I do, I can then prove that these two segments are congruent by CPCTC. Okay, this one's actually going to be pretty simple here. AE is congruent to itself by the reflexive property. Okay? Second thing, let's use black here. Second one, angle F is congruent to angle D because they're both 90-degree right angles. Okay, and finally here, we have two radii. You can't forget that these two guys are congruent here because they are both radii of a circle. So FE is congruent to ED because they're radii, circle radii. And now we can say these two triangles are congruent. Triangle DEA is congruent to triangle FEA. Let's see, let's mark by, let's see, what else did we say? This was congruent to itself. So triangle DEA is congruent to triangle FEA by side, angle, side congruency conjecture. That's side. Oh, I'm sorry. This is, you know what? I didn't even need, I'm sorry, this isn't side, angle, side. It's, excuse me, it's HL. HL congruency conjecture. There we go. There's me being my bad self right there. So check that out. HL means if you have a right triangle, two right triangles here. In fact, that was probably more important. Not saying these are congruent, saying that they're right angles. By HL, HL means hypotenuse and leg. If you have a hypotenuse and leg by Pythagorean theorem, those other ones must be congruent. That's why we limit saying side, angle, side or anything else like that. So by HL, that's true. Step 5 then says what we wanted to say, that AD is congruent to AF up there by CPCTC, or Pythagorean theorem if you want to put that. See. Okay, so those two are congruent. So the basic principle behind this is, and I'm going to go down to this other image right here. If you have a point out in space, doesn't matter if it's here, doesn't matter if it's here, here, wherever else. If you draw tangent lines, those points like this, let's do a different color. Let's use that dotted purple again. If you draw tangent lines such as this and this to the circle, the segments made by the tangent points and the other point outside of there will be congruent. So these two guys are congruent to one another that fit out here and here. Or it doesn't matter if tangent lines are, wherever they are. From here I can draw two tangent lines as well. Those segments are congruent. Okay? So that's the basic lesson behind that one. I would like to do another example here. Let's see how much they give you. They say measure. Okay. Here's all I want to say about this one. Let's do another quickly. Draw another quadrilateral here. So I'll draw one. Let's go from B out to this tangent point, to the center, to this tangent point, back to B. Here's another quadrilateral. Now, you have to remember one thing here is when you draw radii to tangent lines, you form 90 degrees. So these are always 90 degrees. Okay? This is going to help me for the stuff that I talk about later. In fact, I could have just talked about it out there. The fact we're doing this problem a little bit will help. It doesn't matter what this angle is. In this case, I think they say it's 60. If this is 60 degrees, the question is, what is this, right? Now, you could go ahead and say, well, 60 plus 90 plus 90 plus this is 360. But what you do know always is that these two angles here and here will always be 90 degrees. Doesn't matter if it's that example or this example, whatever else. Those will always be 90 degrees because that's the tangent line intersecting with the radius. So the relationship between these two angles here will be the rest of what adds up to 360. So remember, this should be 90 plus 90 plus, and the other two ones, 60 plus x equals 360. If we ignore this 90 plus 90, we can take out 180. If I subtract 180 from both sides, I'll just have 60 plus x equals 180. So here, you're looking at, by the way, this is x. So here, ignore these two angles right here. We know that this angle plus this angle have to equal 180 because these two equal 180 together. And together, they all have to add up to 360. So just these two together have to add up to 180. Doesn't matter if it's those two or these two, which were 90 plus 90, by the way, or on this other page, this angle, one second, well, pretend like it matches there, and this angle. So these two angles right here also add up to 180 degrees because these add up to 90, or because these are 90, so these add up to 180 as well. Okay, we'll do some practice problems right down here. Whoops. In fact, here's, is that what they're talking about here? Sort of. All I know is these are right angles. Like right here, A plus C equals 180. Okay. Angle A plus angle C equal 180. All right, here we go. Oh, perfect. Okay, so alongside that, so let's go ahead and work with what we know there when I talked about that. A plus C is 180. To do these practice problems, you're going to have to know a little bit about that. Okay, so let me write that one time, actually. A plus C equals 180. If A plus C equals 180, then C equals 180 minus A, and A equals 180 minus C. Now, alongside that, another important thing you have to know here is that C is a central angle. Central angle and its intercepted arc have the same degree measure. So if that's true there, then not only does C equal 180 minus A, but the measure of arc BD. I'll put that down. Let's move this. Thank you. Then the measure of arc BD is also 180 minus A. So this intercepted arc right here is also 180 minus this angle right here, because these two add up to 180, and this is the same as that. Okay. Going alongside that notion here, let's do some problems here. Solve for x, knowing that this is 68 degrees. Again, this problem, you might not be able to see what you have right here, so you might want to do some drawings. Okay? Let's draw a center right here. Here are two tangent points. And let's draw the radii to those two tangent points, here and here. Now we know these are both 90 degrees. If these are both 90 and all this adds up to 360, this plus this is 180, so this plus this also must equal 180, this right here, this unknown. We can even call that x. 68 plus x equals 180, so x equals 180 minus 68, which equals 112. So if the central angle is 112, then the intercepted arc right here is also 112 degrees. So once again, going back up here, if that was BD, this is B and this is D, the measure of arc BD equals 180 minus angle A, which would be 68 degrees, which is the same thing, 112. Okay, let's do that one more time. Only it's going to be the opposite way. Here's our arc. Here's our intercepted arc, which is 152. Remember, that's the same as the central angle. These are 90 degrees. This plus this is 180. This plus this is also 180. If this is 152, this is also 152. So x plus 152 equals 180. X equals 180 minus 152. So x equals, 28 degrees. And finally here, these are two tangent lines from a point. We just proved before that these two tangent lines, these two segments right here, are congruent. So x equals 8. This and this both must be the same. Okay, running out of time here. Let me talk about a few more points that are off your stuff here. And I'm going to try and do it as quickly as possible, see if I can. Let's say that I have this thing here, and I'm going to play with it a little bit. I need you to be visually okay with me here. Let's say I put this cross thing right in the center. Here's an intercepted arc right here. The measure of this intercepted arc and this intercepted arc right here, I'm not sure what they are, but let's say that we have some measures here. And then I have an angle, an unknown angle, right here. Let's call it x. I want to find what x is equal to. Let's call this y degrees and z degrees. This is x degrees, by the way. Now, I'm going to move some things here, so these things will be put out of place. But watch what happens when I take this guy and pull it back. It won't be incredibly obvious to you, but if I do pull this back this way right here, and start just going until I make this an inscribed angle. What was lost, here, I'll go back here, and I'm pointing at the screen, that doesn't really work. Watch what I lose in z. What I lose in z, I'm going to gain in y over here. So as I start to move back, watch how z starts to disappear, the amounts that I lose in z, and look over on this side here. As I lose information here, I gain it here. So as I start to pull back, what's lost in z on the right, on blue, I gain in y over in the green. Over, 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 and out. So that z over there that I totally eliminated from my intercepted arcs is now put over here. So as x remained the same, remember this x here did not change. This is still x degrees. This is z degrees, by the way. X as an inscribed angle would be half the measure of its intercepted arc. So x is half the measure of this intercepted arc right here, y plus z. So x equals y plus z over 2. You'll see it that way a little bit as well. So when you see, once again, if I go all the way back, I'm going to do some undoing here. If you see this original angle right here, this x, this is half the measure of this intercepted arc plus this intercepted arc. Because you saw when I moved it over here, it is found, we get that information over here as we lose it here. And then you get all of that right there to show for it. Okay, so x equals y plus z over 2. I want to see if I can keep that. Okay. Moving on from there. Okay, x is y plus z over 2. Moving on from there, let's say okay, so we saw this example here when we had tangent lines meeting with a point out there. So let's call this x right here. Let's call this part z inside here. And outside here, let's call this y. Okay. Here are a couple things that we know. First of all, we do know that x has to be 180 minus z. Okay? We talked about that before. If this is the center, central angles, x plus this angle, which is z as well. If this is z, this is z. X plus z is 180, so x equals that. So we know that much. We also know that y plus z is 360, because if y is this major arc right here, and z is this minor arc, that completes the entire circle. So y plus z equals 360. Okay, I'm going to transform this equation here. I'm going to put z is 180 minus x, because that's also true. If z is 180 minus x, sorry about that. Let's substitute 180 minus x in for z over here. So y plus 180 minus x equals 360. Y plus, here I'll just take out the 360 there. Subtract 180, you get y minus x equals 180, or y equals 180 plus x, or x equals 180 plus y. So as you can see here in this example, x, this degree measure way out here, is the same as taking 180 and adding it to this major arc right here, 180 plus y. So that memorization is going to be kind of difficult, but working with it, you'll start to kind of get an understanding as you go along. There is 180 plus y right there. For the sake of everything, I am very much running out of time here, so it's becoming an issue as I do this. I'll go and pull all this up right here. You start to see this information. So go and take a look at some of this. This x, this thing right here was referring to that other example when it was on the inside. And like I said, I wish I could stress it better. I might do a different video. I might completely redo it for the sake of time and do it better with you. But those are different things. You just have to make sure that you draw things that are missing to help yourself out. And that's the most important take-home thing that you can do with this.